Hello, everybody, and I just wanted to record a few statements about the things we've been talking about to make sure you folks are sort of caught up on the types of things we're talking about here. So, a few things that I didn't get to talk about during the last few lectures that I just wanted to clean up here was some of the evidence we have for plate tectonics, and then a few words concerning the different types of melts we can get with magma, and depending on what environments that magma is produced in. So, as we left off mentioning, right, plate tectonics is just, again, this very powerful theory that mentions that the surface of the Earth, the lithosphere, the crust, is actually broken into a number of different plates that just all move. They're kind of floating around on the mantle relative to one another. In some places, they're coming together, which are convergent plate boundaries. In some places, they're pushing apart from each other. Those are divergent plate boundaries. Some places, they're sliding past each other. Those are lateral plate boundaries, transform plate boundaries. And so just basically all the volcanism, earthquakes, all these spatial patterns are actually due to where the plates are at any given time. So, as you remember, the driving force behind the plates actually moving is just simple convection, right? So you've got the outer core here, which heats up the lower mantle. And remember, this is all solid rock. It's gooey because it's warm, but it's not melted. And so this heat from the outer core gets transferred up. Remember, brighter means hotter. It gets transferred up as a hot spot, right? And then will produce melt once it gets to the crust. Now that's in terms of a hot spot, but as far as plate tectonics, what I want to mention here is that this convection of the mantle is what drives the movement of the continents, right? And so the continents are moving around, they're jockeying, back and forth on the surface of the Earth, mainly because this convection is moving them around. Okay, so and remember, there are a few different types of boundaries. Okay? And so we had already talked about the hot spot. Well, I won't go into that much here. Remember, there is you folks do have the link to the animation here. Let's just remember, with a convergent boundary, you've got subduction going on. So again, you have the oceanic plate, right? Because it's made of basalt and gabbro. It's comparatively dense material. It's subducting below the continental crust, right? There's this accretionary prism here. It's the ocean sediment basically getting scraped off of the plate as it moves down. But remember, this plate has water in it. And water, once it's introduced into this sort of warmer rock, that water actually promotes melting of that rock. And so in these subduction zones, you'll get melting of the rock, which will then produce volcanoes, right? And so these volcanoes will be erupting lavas that tend to be stickier, right? They tend to be stickier because they're made not just with basalt, right? But they're actually melting up through continental crust. And so think of the Andes volcanoes, think of Mount St. Helens, think of the volcanoes up in the Aleutian Islands. Because this melt is melting not just sort of really easily flowing basalt, but it's actually melting more silicate-rich rocks like like continental rocks, right? Like granite, that this melt is going to be much stickier. It's going to trap a lot more gas and vapor, and so that's going to cause an explosion. Just like when you've got dissolved carbon dioxide in a soda bottle, you shake it up, open the cap, you have an explosion. That's exactly what happens here. So when you think about that versus the hotspot situation, which is in Hawaii, right? So you've got a hotspot causing melt at the base of the crust here, and once that melt forms, right, it's coming up through oceanic crust, right? And so there's minimal alteration, right? Because this oceanic crust is pretty uniform. So you're getting basaltic lavas getting erupted. These are not explosive. These are sort of nice, easy flowing lavas. Okay? And so if you think about Hawaii, right? I can walk right up to the lava flows. It's not a problem. Right? These aren't explosive. There's not a lot of water or gas or volatiles. These are mainly basalt, right? Pretty mafic material. Now, if you go to Montserrat, right, that melt is coming up from a subduction zone, so a lot more volatiles. By volatiles I mean water, right, and a lot more things that aren't basalt, right? So some continental stuff, some stuff that's getting scraped off the oceanic plate, and that makes the magma a lot stickier, which makes it trap a lot of these bubbles, and so when it does erupt, you get these really explosive eruptions. So that's the reason why there's a huge difference between Hawaii and these explosive volcanoes. So let me just mention too, seafloor spreading. Okay, now again, this is happening at the mid-Atlantic ridges and also other ocean ridges where new ocean crust is actively being produced. And the reason why there's melt here, because remember, there's not melt. There's only a very small amount of the sort of mantle, asthenosphere, lithosphere that are actually melted, right? Just a few percent. But there's melt generated here because remember, there's a lot of crust overlying these plates, and so when you have these plates moving away from each other, there's a lot less pressure, and so the release of pressure actually causes melt. So you can increase temperature, right? That's one way to cause melt. You can add water. That's another way to cause melt. And you can decrease pressure, right? That's another way to cause melt. So, okay. So those are some things to remember, have in your back pocket. And as far as evidence for plate tectonics, this is the kind of thing that I would ask you on a test, okay? So you can see these ridges, right? These long ridges snaking their way down. These are these spreading ridges. This is where new oceanic crust is actually being formed. And here we talked about in class where the spreading ridge actually got subducted underneath North America, so that is right here. And that's why you've got volcanoes. It's a shallowly subducting slab, and that's why you've got volcanoes here, right? So anyway, that's one line of evidence, is you can actually, with the bathymetry we have now, you can see these ridges, and we know that these are volcanically active. So another line of evidence is if you look where these ridges are, and then you look at the magnetic direction of iron grains. So Earth has a magnetic field, so anytime magma forms, iron within those rocks will orient according to Earth's magnetic field. And Earth's magnetic field goes through a number of reversals. And so all these data are really telling you is that these magnetic reversals actually show up in the rock. And again, if you don't quite understand this, I would do a bit of research on magnetic reversals and its evidence for plate tectonics. That the magnetic reversals that are preserved in the rocks are another line of evidence that plate tectonics is a good description of what we see in reality. And this is a heat map here, and not only do we see really warm spots along the spreading ridges as you would expect, we also see really cool spots along the margins. Again, that's what we would expect. And, I mentioned earlier that we can actually measure the movement of plates, and here we do have measurements of movements, which makes sense. And, some of the research that I did in the Caribbean was actually working on measuring these movements. And you also remember the video we watched that showed Pangea, being together, then coming apart. Well, we have continuous fossils that go across continents, right? And so they show us that continents were connected at one point. So we have these continuous fossils, animals that couldn't swim across oceans, right, in the current configuration, but we have their fossils represented as if the continents were together at one point. So again, that's another piece of evidence. So another question we might have is, okay, so Earth has plate tectonics, and as you'll continue to learn, plate tectonics is super crucial for life on Earth. Well, how did it get started? What's important for plate tectonics to start? So one thing I want to mention is, think about the early Earth. It was all molten, and you started getting these cratons forming. And so they were forming during different eras, but in the early Earth, and again, these are representing where they are now. In the early Earth, these are these cratons, right, that started to form. Cratons were just lumps of granite that were kind of floating in the, on the mantle, basically, right? Big chunks of granite floating on the mantle. So as these cratons began to assemble, then you started getting interesting behaviors. You started getting interesting behaviors where you started getting these rifts opening up. And I think the best way to show it is this is an image from a video. And so the video I'm going to show you is as the lithosphere, as the oceanic lithosphere kind of gets colder and denser and starts to kind of fall down into the asthenosphere, you start actually pinching off these continents. So let's go to this. So this is a story here. So, okay. 45 million, after 45 billion years of spreading, the pink is the region where the mantle underneath the Earth continent, the early continent, has melted, facilitating spreading and the initiation of plate tectonics. Okay, so we've got some partial melting going on. Okay, so just a few things to pay attention to in this article. Until 3 billion years ago, the Earth's crust was immobile. So what sparked, plate tectonics? And they suggest it was triggered by the spreading of early continents. So this eventually became self-sustaining. Okay. Okay, so this movie here tells an 87 million year long story. It shows an early buoyant continent, right, made of a residual mantle in green and continental crust in red, slowly spreading toward the adjacent immovable plate, right? So after 45 million years, a short-lived subduction zone where the plate goes under develops. This allows the continent to surge toward the ocean, leading to the detachment of a continental block, the starting step in the movement of the continental plates or plate tectonics. So let me just stress to you that this model is just parameterized by physics and the physical laws and the properties of the materials. And so basically having some of these early continents kind of surging and spreading forward promoted the breaking up of the further breaking up of the continents. So let's just look at so you can see, right? So let me actually, can I slow this down? No, I don't think so. Let's play that again. Okay, so you can see the continent riding up over that plate. So again, and as the plate subducts, it surges forward, and you start to get this breakup here, right? So you're actually forming additional continents here. And so let me just mention a key to plate tectonics is, you can see in this video, which is something we should talk about here, is differing densities of rocks, right? So in order for whoa, in order for subduction zones to set up and to be self-sustaining, right? There's got to be a difference in density. And so here we have a more buoyant continental crust, coming up against a denser, less buoyant oceanic crust, right? And so when they meet together, because this is denser, it will go underneath. And so the other thing I wanted to mention, which is actually pretty interesting, is we'll go back to that heat map. Okay? Oh, here's the heat map. Oh, let's go back. What the heck? Let's go back to the tectonic. There we go. Let's go back to this plate movement movie. And something I want you to pay attention to here is you've got the continents coming together, right? Let me speed it up for us. Okay, you've got the continents. Okay, we're actually going back in time still, so... Okay, now we're going to start going forward in time. So we've got Pangea, right? And then we're starting to break apart, right? North America and South America are going to break apart from Africa and Europe, right? And you've got Antarctica moving towards the pole, and you've got India, right, moving in for its collision with Asia, right? And so we're moving to pretty much the present day configuration. And so remember, what we've got going on here right now is we've got a spreading ridge right here, right? We've got subduction zones. Well, sorry, we've got another spreading ridge here. We've got a subduction zone set up here, right? And here, remember, we've got volcanoes in the Andes. We've got volcanoes on the western U.S., right? And so, right now, there's subduction here, there's spreading here, which is meaning the Atlantic Ocean is going to be getting bigger, the Pacific Ocean is getting smaller. But let's see what happens when we run it forward here. Okay, we're getting to present day. There's an ice age. Okay, now we're moving forward in time. Okay, so you see what happens, right? They're going to keep moving away from each other. Okay, makes sense. Oh, but now things are sucking back, right? And so what's happened there is that the ocean crust that was against these continental margins, right? This was just attached, right? There was no subduction zone here before. That ocean crust has gotten cold and dense enough that it's actually broken free, and you've got subduction zones forming all along these continental margins, right? Possibly here too. And so because you have those new subduction zones, now instead of making the Atlantic Ocean bigger, you're going to be making the Atlantic smaller and the Pacific bigger. So as we go forward, as we go forward, 250 million years into the future, we end up with another supercontinent, right? And then remember, because this continent is covering so much, right, that heat is going to build up. This is like a big blanket on the Earth. And heat from the inside of the Earth is going to have a hard time escaping, can't get out, and it's going to start breaking this continent up again. So that's why we have these periodic, supercontinents, then broken up, supercontinents broken up. And so we just happen to be living in a time when the supercontinent has been broken up and we're spreading kind of farther apart. Okay, so that all goes back to this image right here, right, showing where the warm and cold areas are, right? So you can imagine, as this keeps spreading, these will just get colder and colder, right? And therefore denser and denser until finally, they start to subduct underneath the continent. So that's the idea behind this cyclic nature of supercontinent break apart, right? And so we have these cratons. We have a mechanism through which these cratons started having a plate tectonics system going, and then was able to be self-sustaining. And we'll sort of leave it at that for now with plate tectonics. So please do visit this link, but also these two links, right? Make sure you visit these links and read the stories. Try to get an idea of how plate tectonics developed. Okay, so a few things I want to mention that we mentioned earlier that I just want to hit on again is what factors are most important to actually get this melt. And so remember pressure. So when rocks are under high pressure, it takes more heat to melt them than when they're under low pressure. So if heat stays constant, but pressure is released, then they'll all of a sudden start melting, right? So that's the mid-ocean ridge. Temperature. So when you have a hotspot plume coming up from the outer core boundary, that's adding heat, to just below, underneath the crust there, right? And so as it adds heat, then you end up getting melt, and then water. So at subduction zones, you have the addition of volatiles, mainly water, and water will lower the melting point of rock. So again, you will get melt. So those are three different places where you actually get magma and lavas erupting from those areas, right? And we also have to take into account, the different melting points of the different minerals, right? So that's what Bowen's reaction series is all about, right? So, olivine, it takes a lot more to melt olivine than it does to melt biotite. And these guys are the first to melt, right? And so you can imagine partial melting is an important vocab word. Partial melting, and what partial melting means, let's say there was a rock that had all of these things, right? Let's say there was a rock that had all these. Maybe we've got olivine, right? Or sorry, we've got a rock that's got all these, so peridotite. And so if you just applied a little bit of heat, you'd partially melt some of these minerals. So you'd melt these, and so your melt would end up being enriched in these minerals that tend to melt first, right? So partial melting is if you don't apply enough heat to melt all of these minerals, if you just apply enough heat to melt some of these minerals, then your melt will look like this, right? And it won't look like this. So that's the idea of partial melting. And that's how that's the thought on how we originally got cratons to begin with. And then I wanted to add this figure to sort of help you folks. I wanted to flesh this out a little bit more. And so if you're like 100% olivine, right, or close to 100% olivine, with a little bit of pyroxene and calcium plagioclase, then you're a peridotite, right? That's a type of rock, peridotite. That's what the mantle is peridotite, right? So that's what we call ultramafic. And so really dark rock, really low on silica. And so remember that the more silica you have, the stickier the rock gets. So the more likely you're going to have explosive volcanic eruptions. And so really low on silica, low on sodium, potassium, because there's not a lot of feldspar, right? And a lot more iron and magnesium specifically. That's sort of the definition of ultramafic. And so, mafic, you're kind of moving down, and this is where your gabbros, so the intrusive igneous part of the ocean crust, and basalt, the extrusive part of the ocean crust. And so your gabbros and your basalts, they're mafic, they're in this area. They don't look like the mantle. So again, they're much more similar to the mantle than granite, but there has been some partial melting so that they don't look like the mantle, right? There's been some partial melting so that they have a little more plagioclase here, right? And, much less olivine, right? And then if you move down to the intermediate rocks, again, this would be with more partial melting, right? You've got an andesite or a diorite. So again, you're going to be increasing your feldspar. Then as you get over here to these granites, rhyolites, so rhyolites and andesites, these are both associated with explosive eruptions, and that's because you're increasing the silica, you're getting more felsic like rocks, right, or melts. And so this is basically how I just wanted to help you folks interpret this diagram here. And speaking of melts, what can affect the chemistry of the melt? So one thing is the source of the melt itself. Where are you getting it from, right? Is it from a hot spot heating the underside of an oceanic plate? Is it from a hot spot heating the underside of a continental plate? Is it from a mid-ocean ridge in the middle of, an oceanic plate? Is it erupting up and through a continent, right, and getting partial melting going on there? And another aspect is fractional crystallization. So, and this should be a bullet point all on its own, so I'll fix that. But fractional crystallization and gravitational differentiation, all that means is what we've been talking about in lab, is that, again, according to Bowen's reaction series, some minerals will crystallize first. And if they get a chance, they don't always get the chance, but if they get the chance to leave the melt and deposit, and become rocks, solid rocks, then the melt will become deficient in those first minerals to crystallize. So again, if I say fractional crystallization, that all that means is that a fraction is becoming crystallized. So this is just going back to Bowen's reaction series. That's fractional crystallization. And gravitational differentiation, all that means is gravity is causing those crystals to settle out. So that's all I had for this session. Please do make sure that you are staying up on the reading you need to do, as well as making sure that you are paying attention to the other videos and audio lectures that I might put up. All right, have a good day.